Let me say also, I didn't see the email, but I'm up against a lot of things, so I didn't get to it this morning. There is no new assignment today. I'll probably post the next time sometime next week. For this assignment, with all freedom in the world, you can turn it in next Friday, so that's fine. And that'll give you all a chance to catch up with me as well. So, okay, questions. So this was the last thing we were working on, and I believe we proved. And I'm going to skip the other direction for the following reason. Other direction. Easier and is almost entirely repeated. Will be contained essentially the proof be contained in the net result, which I'm going to put it as unnumbered. I was going to add that to my notes this morning. Didn't have time, so I'll have to do it afterwards. I'm going to go ahead and throw this here. Proposition unnumbered. But perhaps as a field here, then, well, let's see. Suppose that you have an irreducible polynomial over something, right? Irreducible is going to be important. Then, if f of x is not then the derivative is, I'm going to put it in the register, is identical to 0. So this kind of really kind of puts an exclamation point on this. Not only is the GCD of f and f prime not equal to 1 if it's not separable, but in fact, if it's irreducible and not separable, then the derivative is 0, uniformly 0. So why would such a thing be? Suppose that, and even though I am going to use this result, but the other direction is more straightforward, even than what we went through last time. Suppose that f of x is irreducible, but not separable. By previous, I guess it's 2, the GCD of f and f prime is not equal to 1. Correct. So, what does that mean? Well, no. So let's remember that f of x is actually an element of f bracket x. And what do you know about the ring structure of f bracket x? It's a pretty important kind of domain. Yeah, very good. So, in particular, it's good. So if f of x is irreducible, then f of x is prime. Right? Because irreducible polynomials, irreducible elements that are not 0 in an integral domain are prime. Okay. So we know that since it's not separable, GCD of f and f prime is not 1. So there exists d of x of degree bigger than 1, such that d divides f and d divides f prime. So in particular, this means that f of x is d of x, a of x. Agree? But f of x is prime and irreducible. So this means that a of x is a unit, which means a constant. So f of x and d of x are the same. Without loss, generally what I mean is f of x and d of x might vary by a constant, but they're essentially the same. Agree? This means that f of x divides f prime of x. But either f prime of x is 0 or degree of f prime is strictly degree of f. This second one is ridiculous because you can't have a polynomial of higher degree dividing a polynomial of lower degree. So you're forced f prime of x must be the 0 polynomial. This is an important observation. I think if you have a polynomial that's both irreducible but it's not separable, its derivative must be identically 0. Any questions on that? So I'm going to give you something that I mentioned a couple of times before, but we're going to rip off from this really quick. Theorem. And I will remember this one. Got to remember. Oh, I guess a couple of conversation. Suppose that an algorithm and the characteristic K is 0, then it's separable. Okay. So this is what I promised before. If you have any extension of degree 0, then you're automatically separable. Let me give you a quick proof of this. What you have to do is show that every element is separable. So let U in F have minimum polynomial. F of x, which is say x plus a n minus 1 plus n minus 1 a1 x a 0 with n greater than or equal to 1 and what is fun. Notice that every element of K itself, is a root of the polynomial x minus k, so no problem there. And of course, if you're an element of U that's not in K, then by the algebraic hypothesis, there has to be some polynomial and takes me mine. Notice that f prime of x is n x n minus 1 plus a bunch of other things. Really not so important. And notice that as n greater than 1, f prime of x is not identical to 0 because that term at least has to survive. So characteristic 0, everything's set. Proposition. That's so. And since it's separable or minimal polynomial of u is separable, then u is separable. Okay, any questions? Okay, definition. Okay, so let's go from one extreme to the other, shall we? What does it mean for a polynomial to be separable? It means that it's whenever you go high enough in the field where it splits down into a product of linears, those factors are all distinct. And a separable element is an element that is a root of a separable polynomial. What's the other extreme, do you think?
It's the same.
That's right, where the minimal polynomial is in fact a single linear polynomial to a power, right? That's the other extreme. And we're going to define that here. We're going to call such a thing purely inseparable. Let K and F be an extension. An element U and F algebraic K is purely inseparable over K if its minimal polynomial factors as, let's say, U is an F, x minus u from n, and fx. The extension f over k is purely inseparable if every element is purely inseparable. Let K be a field. Somebody give me, for any field K, give me a purely inseparable extension. And you know, there's actually a little clue in my question that might help you out. Notice I did not say that K, I didn't make any specifics in this except K is a field. I didn't specify that it's not a characteristic 0. Any field has a purely inseparable extension. The problem with that is it's not algebraic.
Yes.
Stop thinking like good graduate students. You need to think like a smart aleck to answer this question. What's that?
You make it happen.
No, you don't even have to do that. How about this? What's the easiest extension field? Okay, you can think of. Right, because any element is already in K, so the minimal polynomial is X minus K. Now I bring this up for a point because there's a curiosity. The extension of any field over itself is purely inseparable and also separable. And there's a method to my smart aleck example in the following sense. K over itself is a separable extension because any irreducible polynomial has degree 1, so it has to have distinct factor, right? Because there's only one. It's also purely inseparable because the minimal polynomial is of this form with n equal to 1. Right? It's going to turn out that if I walk up to you on the street and give you a field, then you're going to have what we call a purely inseparable extension of that field and a separable extension of that field. And both of these, or either one of these, could be trivial. And the intersection of those is the base field. So the extension over K, think of us, what kind of extension can be both purely inseparable and separable? And you get the base field. And because of that, we get to kind of break things up in a certain sense. So I'll follow the social. Yeah. And I'll go through the details of this a little bit. If K and F are fields, and of course F is algebraic. And actually, I don't because all I want to do is talk about the element, right? It can have any extension field, and U and F is both. Well, actually, so say here, comma, U and F is both separable and purely inseparable. Over K, if and only if U is in K. So any element of an extension field that is both separable and purely inseparable is in K, and conversely. We have shown that basically this direction, right? Now suppose this previous example. If suppose U and F is purely inseparable, this is basically just a matter of definition here. Then, if it's purely inseparable, it has to be algebraic by definition. Then its minimal polynomial must be a form X minus U to the n, but as U inseparable, all the all the linear factors must be distinct, so therefore, x minus u is in kx. Because remember, this minimal polynomial actually, when you multiply it out, when you multiply it out, this must be a minimal polynomial coefficient in k. Well, n is 1, and that forces that last coefficient to actually be k. Okay, any questions on that? Now here's kind of a cleaning, if you will. Point 6. Suppose the characteristic of K is equal to P. So here we have prime characteristic. And F is an extension. So of course, F must also have characteristic P. If U is algebraic over K, then U to the P to the N is separable over K for some N in the back. Okay, so this is, I find this little limit here kind of interesting because here's what's going down with this. This algebraic U may be the root of some polynomial. It might be a huge mess, right? It might have some linear factors that aren't distinct, et cetera, et cetera. So this algebraic element may not be separable. So its minimal polynomial may have some crazy multiplying. What this says is you can jack U up to an appropriate high power P, and even though U may not be separable, all of a sudden this one is, right? Which is really cool result. So big enough power, you get to be separable. And of course, as you might glean, the P here, same as the characteristic, is going to be important in the sequel. So if the degree of U over K is 1, then done. So, because of course, that means that U is already in K, and so it needs to separate itself. And well, I could even take M0, but it doesn't matter. U to the 1 in this case is separable, but of course, if U is separable, then U is also separable. So either way you want to do it. So now suppose that we have the minimal polynomial. F of x, minimal polynomial. U and degree of F is bigger than that. Let's further suppose U is not separable. Because again, let me point out that if U is separable, you're done, because you could just take the first power of U and there you go, it's separable. It's already separable, you're good. Agreed? So let's suppose this is not separable. Earlier proposition. What can we say about f prime of x? It must be 0, right? Because f being the minimal polynomial is irreducible, the element's not separable. So this is 0 polynomial. Now let's go a little bit further than that proposition that does. So let's say that this is well, let me make it easy to say it's mod xn plus an minus 1 xn minus 1 a1 so 0. This is the minimal polynomial. Now, what do we know? We know that the derivative of that is identically 0. I've written this too general. Can somebody streamline what this polynomial must look like? Well, so when I take the derivative, this is n x n minus 1 plus n minus 1 a n minus 1 plus n minus 2 plus 2a2x plus a1. Now this has to be identically 0. What does that mean about the leading coefficient? This means for this to be 0, then this must be 0 here. What does that mean about n? N is a multiple of n. What does that mean about this right here? Well, if n is a multiple of p, then n minus 1 is not, right? So that means an minus 1 must be 0, right? When's the next time you can have something to be 0? Either the coefficient here is to be 0 or the exponent must be a multiple of p. So in particular, f of x must be a polynomial in x to p. Right. That's the only way that the derivative can be identically 0. Right. Let me give you something a little formal that's less than convincing. So I just kind of did something fast and loose here. How can we prove this? Well, if not, then f of x has a largest degree term. Let me make that more precise. A largest degree non-zero term. With degree not a multiple of b. Right. So f of x looks like this. It's got a k x to the power. This is the largest term where ak is not 0 and k is not a multiple of p, right? Everything else, the exponent has multiple p, right? So when you take the derivative, then all of this stuff up here goes to zero. Because you've got multiple p in every exponent. And this goes to ak times k x to the k minus 1. AK is not zero. K is not a multiple of p, so this is a non-zero element. Right? This is a non-zero coefficient of this thing right here. And so this derivative has at least this term surviving, so it's not identical to zero. Everybody okay now? Okay, so that's a key observation, is that f of x must be a polynomial on the variable x p. So f of x is actually let's say p of x to the p. And so notice that u to the p now algebraic of degree less than the degree of u. So we inductively assume that since the degree of up is less than the degree of u, we inductively observe that u to the p times some p to the m, which is u p to the m plus 1, is separable. And we're going to find out. In the case 0, we did this right here, and now we use the u to the p, since this is a degree less than u. A power of this must be separable, so this gives you your power 4. So that's a really cool result. Any questions? Okay. But then the following conditions are number 1, f is purely inseparable. Okay. 2, the irreducible polynomial minimum irreducible polynomial of any u in f takes on the form it's actually very simple, right? It's actually just a binomial. large power here, the power must be P to the N minus A, and of course, this is in K of X, I mean, A is in an element of the base field K. If U is an F, then U to P to the N is in K for some N. Number 4,
Should 2 be like the minimal polynomial or? Is that
which one right here?
number 2? Yeah.
It's the same thing. If it's irreducible, it's minimum.
So why are we usually calling it the minimal polynomial? So now it's calling it.
A minimal polynomial is the smallest degree polynomial satisfied by U, right? And that minimal polynomial will be irreducible. You can call it minimal. Number 4, the only elements of F separable over K are the elements of K. So in a purely inseparable extension, that's probably not too surprising. The only things that are actually separable are the elements that are in K itself. And F is generated over K. By a set of purely inseparable elements. Okay. So let me let's look at some of this here. Let's kind of flash through some of this. 1 and 2. Okay, so F is purely inseparable over K. What does that mean? By definition, it means every element of F is purely inseparable. And so if U is an F, then U is purely inseparable. So it's minimal polynomial. Right? But what do we know about this N? By our earlier observations. Because after all, there's a power of this that is there's a power of U that's purely inseparable. Well, let me do on this. That N is a multiple. More detail. N is a multiple of P. And in fact, it goes further than this. The power of the power I believe is in K. So And so, the irreducible and minimal polynomial takes on its form, where your A is this. Two implies three. I think it's fairly obvious, because so I'll let you check that out. That might be obvious. If U and F, right, so so suppose since U, the P to the N is in K, then minimal polynomial of U over K is a divisor of X to the P to N minus U N. Now notice that, of course, U is a root of this polynomial. This polynomial is actually in KX. And this polynomial, of course, is X minus U to the N. Now, this divisor of the polynomial from our argument earlier, so minimal polynomial must actually be a form it must be a smaller, perhaps smaller, maybe equal prime power. But if we're assuming that U is separable, then M must be 0. So minimal polynomial in KX is X minus U to the 1. So U is in K. So that means the only separable elements are the ones that are already in K. And for this one, it says F is we need to conclude that F is generator of K by a set of purely separable elements. Well, take the set of all purely inseparable elements over K. All right. Well, let's take all the elements. Let me just say this. Take the set of all elements of minus K. And I claim that every element that's in F but not in K is in fact purely inseparable element. How do I know this? U is in F minus K, then U to the P to the N is second for some Not one. Use it. That's one of our results we had earlier, that if you take a big enough p to the nth power of some element, it becomes separable eventually. But that means u to the p to the n is actually bad because it's second. Yeah. And so we have that u to the p to the n equals a into a, and so u is a root of x minus u to the n x. So u is purely stable. Plain and simple, because it's minimal polynomial has to divide that. So maybe you've got a lower power, but in particular, it's a power of just one linear. And so since every element in F that's not in K is purely inseparable, it's clearly generated by a set of purely inseparable elements. Just take K and take a big shovel and start shoveling in all the elements that are not in there, and there you go. I mean, it's really kind of overkill. And I guess 5 implies 1. I think that comes full circle on this. I guess we really need to convince ourselves. So actually, so let me say something else. So show sums and products of purely inseparable elements are purely inseparable. So that's how you finish that, because then just take all those elements and generate sums and products of those purely inseparable elements are purely inseparable, and hence you'll get statement 1. So let me give you a corollary. Again, we're assuming the characteristic of K is equal to P bigger than 0. And F is a finite dimensional, purely inseparable extension. Purely inseparable extension. Finite dimensional, right? Okay. Then anybody want to take a stab at this? So it's finite dimensional, so this is going to be some integer, right? But it's a special form, right? That's exactly right. Right? Because if you take any element in F that's not in K, its extension will be of P to the N. If you believe this thing about sums and products of inseparable elements, it's that. And so actually, since it's finite, it has to be some power of P, because all the intermediate fields will be some smaller power of P. And so the only thing that is only fillable out powers of P is powers of P. Okay. Any questions? All right, well, think about the math club today. Other than that, y'all have a great weekend, and we'll see you on Monday.